welcome to this event. A couple of things. I know some of you probably might be really excited for the presenters that are up here. Try to keep it down a little bit. We have other presentations going on, so we want to be respectful to them. We also want to be kind to our students up here presenting. So, you know, they might be a little nervous, so please be respectful for them too. And yeah, treat everybody fairly. All right, thank you so much. So without further ado, I'd like to introduce Tyro Pautee from Arizona State University.
Okay, so my name's Ty, and I'm going to talk to you a little bit about sedimentary geology, how we can use that to look at past events, and we're going to do that in southeastern Arizona. So for some background, just general, Arizona starting around 30 million years ago has been subject to significant tectonic extension. And what that means is basically the crust is spreading apart, it's breaking into these fault blocks that tilt and collapse against each other, and that creates these different ranges and basins. And in the basins, you get deposition of sediments, and those sediments are a product of the time, so they're recording the conditions of what's happening. Around 5 million years ago is when tectonics stops, and the basins keep filling until they overtop, and then you get formation of river systems that stops deposition and they start to erode. And if we look at my study area specifically here, this is the Pinaleño mountain range. This is the highest point in southern Arizona, and I'm working on the northeast flanks on these remnant basin fill sedimentary deposits. There's a legacy of work here, so my mentor Kellen and Arjun Heimsath, who's at ASU, a bunch of their students over the years have worked in the range, looking at erosion and landscape evolution. And whenever they've gone there, they see this pattern in the landscape where there's a bunch of these dissected mesas. And the bulk of this is mainly fine-grained sediment like sand and mud, but they always see this really tiny top layer of gravels. And it begs the question, why is that there? So usually when we see such a drastic vertical change in grain size, it tells us maybe there's something in the climate that has changed during deposition, like the temperature or precipitation changes, and that changes what type of sediment is being produced. And then this is capping everything in the basin, so why is it there? And there's actually different levels to the surfaces, different elevations, so why is that? And my job here is to sort of explore the relationship, what is the gravel cap, what does that mean, and how is it related to the underlying fine-grained stuff? And I'm exploring that through two hypotheses, two extremes really. So the first is that climate-driven hypothesis, and this is completely a vertical change. It's an extreme to where it goes from fine to coarse everywhere. The other hypothesis, alternatively, is that instead of a vertical change, it's more side to side. So both the gravels and the fine-grained stuff are there next to each other at the same time, and something happens at the very end of deposition that pushes the gravels out over the top, and we're only seeing this part of that sequence. And the important thing here is that in order to test these hypotheses, what we're looking for is here. Can we find evidence of the gravels lower in the section, and can we find them interacting with the fine-grained stuff at the same time? So in order to actually do this, we start by doing planning and analysis of the topography. So using LiDAR data, which is like satellite topography, I can look at the landscape from the top, but also constructed 3D surfaces. And the main thing we're looking for is exposures of the sediment. So almost everything out there is covered in this thick layer of debris, so we need to see through that and find areas where that's exposed. So in order to do that, we built a slope map, and we symbolized it so that it pops anything that has a high slope, it's a cliff or like a landslide scarp, it pops it out as red. And after tweaking with field observations, we got this 35-degree threshold, which seemed to really be good at telling us where the exposures are. So we go through and we mark all of these exposures that seem like they're interesting. And then we go through, we look for any interesting topographic patterns, I'll cover that later, and then we can also differentiate these different levels of the fan surfaces. And then all of this information comes in to the creation of an efficient itinerary. Because fieldwork is expensive, it takes time, so in order to make the most of this opportunity, we rank the different priority of where we want to go. We find how easy it is to access. Is there roads? Is there private property blocking it? And then we plug that in and we create a field itinerary like this. Now, this is from January, the last time we went out to do field work. Each of these blue lines is a different road that I have outlined as this is the best way to get in. It doesn't seem like there's any fences blocking it. And each one of these pins is a different exposure that I noted on the topography. It's like, this looks interesting, I think there's something worth looking at here, so I'm going to try and go and explore all of these areas. And the actual exploration, it's pretty simple. So when we get there, we just do qualitative observations of grain size, sedimentary structures. From that, we can interpret the facies or the depositional environment. Was this deposited in a lake? Is it a stream? Or is it alluvial fan? And we got to these exposures just on foot, hiking around, driving in a truck. We can see it through binoculars, or if we have to send a drone to go take a picture, it's too far away. And put all these different points down. We have an app that geolocates all these to GPS coordinates, puts either pictures or our notes in, and we build sort of a patchwork of these different observations that then can act as like, we can see the geometry of the different units, then we can infer their relationships and result in a geologic map. Now, the results here, this is just the landscape here, and each one of these points is an observation that we put down with our notes, pictures, and our classification of the sedimentary deposit. And when we classify this into a map, we get something like this. Each one of these colors is a different sedimentary unit. The red is closest to the range front, there's yellow further out, but the important thing here is that there's this orange band in the middle between them. And I'm gonna go through the units here. So the yellow that's farther out, that's the fine grain stuff that we saw at the very start. That's the lake beds and stream deposits, sand and mud. The red stuff close to the range are this really coarse alluvial fan deposits in those gravel caps at the very start. But what we found that we didn't know before is this transition zone of these, where you have both the fine and the coarse together interbedded. And this is really interesting because it's traceable all around the range, especially on the north side. And then we can also interpret that it's down here. I'll talk about that in a second. But it's showing us that there is sort of an interaction between the two, fine and coarse. We also found these interesting topographic features, so just remember these. One of them is very ledgy, there's like little ridges in the landscape. The other would be these mesas are surrounded by these lumpy terraces. And then we also found that that gravel cap, that highest one, correlates with the alluvial fan deposit, so the red is the same as those. So, and there's levels, at least 4 levels below that seem different, and I'll talk about interpreting that here in the discussion. So those ledges that I mentioned, that's evidence of the transition zone where there's coarse and fine stuff, there's differential erosion. We can see that in the topography, and then whenever we see that in the map, we can just sort of interpret that it's there even if we weren't there in person. The same thing with those lumpy remnant terraces around the mesas, those are the fine grain deposits. And then even the coarse gravels, the alluvial fan, the red zone, has this really smooth lobe-like features that's less diagnostic, but it still tells us maybe what we can expect there. And from that, we can build, we have the map, we can interpret what's happening in the subsurfaces, what we're interested in. Now that orange zone in the middle here, in between the two interfering things, that is evidence directly for hypothesis 2, that both of them are there at the same time, the contact between them is migrating, and then because we know that the gravel cap correlates with the red, something at the very end pushes them out across the rest of the basin. We think that that is the end of tectonics. The basin fills up, there's no more space, so it keeps going. And the important thing here that I'd like to note is that it's really interesting to look at a landscape, get into the details, but then just looking at it, you can interpret a story. This is at least 5 million years of tectonic and erosional history, and it's just really interesting to look at this kind of thing and see the modern Gila River and be able to see the story in the rocks in the landscape.